Welcome you in the lecture series of random processes, detection and estimation. It is 21st lecture of this series. In previous lecture, we have discussed about energy detector and an estimator correlator detector, which are useful to detect the random signals. In this lecture, we will discuss about Bayesian linear model, and the outline of this lecture are: we will discuss about detection for Rayleigh fading sinusoidal in white Gaussian noise, and incoherent FSK for multipath channel. And in the objective of this lecture, you will able to explain why Bayesian linear model is used and what is the quadrature matched filter or an incoherent matched filter. So let us start with the Bayesian linear model. Let the DC level in white Gaussian noise has two hypotheses. H0 corresponds to xn is equal to omega n, means under hypothesis H0 there is only noise, no signal is present, and under hypothesis H1 xn is equal to a plus omega n, where small n is equal to 0 to 0, 1 to n minus 1. Or you can say x under hypothesis H0 it will be omega, and under hypothesis H1 you can write it as a1 plus omega. When a is deterministic constant, then we can use classical linear model to detect the deterministic signal in white Gaussian noise. And we have already discussed this classical linear model in lecture 19 and 20. In some situations, A may be modeled as a random variable. For example, detecting an age of an object in an image, then the detection of the random signal in white Gaussian noise could also be simplified with the use of Bayesian linear model, where the random variable A will be the Gaussian random variable with mean 0 and variance sigma a square, and it is independent of omega n. And let the Bayesian linear model is x is equal to h theta plus omega, where x is n is to 1 data vector, that is x is x0 x1 to xn minus 1 transpose matrix, and h is the known np observation matrix, and theta is t is to 1 random vector of unknown parameters, with theta is the having the PDF of normal distribution with mean 0 and covariance matrix C theta, and omega is 1 is n is to 1 noise vector with the normal random process with mean 0 and variance sigma square I, and independent of theta. In Bayesian linear model, let expected value of theta is not equal to 0 and CW is arbitrary, covariance is arbitrary here. Now the detection problem can be expressed as in two hypotheses. H0 corresponds to x is equal to omega, and H1 under hypothesis H1 x is equal to h theta plus omega. For NP detector, we know S is equal to h theta, and it will be the normal random variable with mean 0 and covariance matrix h c theta h transpose. So the NP detector in random signal case, that is estimator correlator detector, decide H1 or H0 if the test statistic is equal to x transpose CS into inverse of the matrix CS plus sigma square I, x greater than less than threshold value gamma double dash, or you can write test statistic as x transpose S cap is equal to x transpose h theta cap greater than less than threshold value gamma double dash, where theta dash is the minimum mean square error estimator MMSE, of theta, and we will discuss this kind of estimator in the estimation section. An important application of this result in the Rayleigh fading channel. Let us consider one example. Let us two hypothesis, H0 hypothesis. It is corresponds to xn is equal to omega n, means under hypothesis H1 there is no signal, only noise is present there, and under hypothesis H1 the signal xn is equal to a cos 2 pi f0 n plus phi plus omega n, where f0 is between 0 to 1 by 2 and omega n is the white Gaussian noise with variance sigma square, and a and phi are random variables. So instead of assigning a PDF to a and phi, it is more convenient to note that here Sn is equal to a cos 2 pi f0 n plus phi, and cos a plus b, it will be cos a cos b minus sin a sin b. So we can use here as Sn is equal to a cos phi cos 2 pi f0 n minus a sin phi sin 2 pi f0 n, and if I consider a cos phi is equal to alpha 1 and minus a sin phi is equal to alpha 2, then Sn will be alpha 1 cos 2 pi f0 n plus alpha 2 sin 2 pi f0 n. So now assign the PDF to alpha 1 alpha 2 transpose, and here the signal model is now linear in a parameter alpha 1 and alpha 2. From the central limit theorem we can assume that theta will be theta is the transpose of alpha 1 alpha 2. This means this is the column matrix alpha 1 alpha 2, and it will be the normal random variable with the mean 0 matrix, and variance the variance matrix is sigma s square into I, identity matrix, and theta is independent of omega n. Sn is wide sense stationary Gaussian random process. Since expected value of Sn, it will be equal to expected value of alpha 1 cos 2 pi f0 n plus expected value of alpha 2 sin 2 pi f0 n is equal to 0, and correlation between the signal Sn plus k means expected value of Sn plus k, it will be the expected value of alpha 1 cos 2 pi f0 n plus alpha 2 sin 2 pi f0 n into alpha 1 cos 2 pi f0 n plus k plus alpha 2 sin 2 pi f0 n plus k, and it will be equal to, you can say it is expected value of alpha 1 square cos 2 pi f0 n into cos 2 pi f0 n plus k plus alpha 2 square sin 2 pi f0 n sin 2 pi f0 n plus k, and it will be equal to sigma s square into cos 2 pi f0 n cos 2 pi f0 n plus k plus sin 2 pi f0 n sin 2 pi f0 n plus k, and it will be equal to sigma s square cos 2 pi f0 k. So Sn is wide sense stationary Gaussian random process with autocorrelation function ACF sigma square is the autocorrelation function sigma s square cos 2 pi f0 k. Also you can show that the PDF of A means under root alpha 1 square plus alpha 2 square is the Rayleigh, or we can say the PDF of A when A greater than 0 it will be a by sigma s square is to the power minus a square by 2 sigma s square, else it is 0. When a less than 0, it will be 0. And the PDF of phi tan inverse minus alpha 2 by alpha 1 is uniform over 0 to 2 pi, and a and phi are independent of each other. The term Rayleigh fading refers to the amplitude PDF because the amplitude is the Rayleigh distribution. The channel model is referred to as Rayleigh fading channel model. With these assumptions, the observed data follows the Bayesian linear model x is equal to h theta plus omega, where the matrix H will be with the elements 1 cos 2 pi f naught to here cos 2 pi f naught n minus 1, 0 sin 2 pi f naught sin 2 pi f naught n minus 1. Theta is having the normal distribution with mean 0 and variance sigma s square I. Omega is the normal distribution with mean 0 and variance sigma square I. And theta is independent from omega. Now for the detection of the sinusoid, the NP detector decides H1 or H0 if the test statistic X transpose H C theta H transpose into inverse of the matrix H C theta H transpose plus sigma square I and X, and this test statistic can be given as sigma s square X transpose H H transpose and the inverse of the matrix sigma s square H H transpose plus sigma square I into X greater than less than threshold value gamma double dash. And here gamma double dash is the 2 gamma dash sigma square. And using the matrix inversion lemma means the inverse of the matrix A plus B C D, it will be equal to the inverse of the matrix A minus inverse of matrix A B, and inverse of the matrix A inverse B plus C inverse into D and inverse of the matrix A. Now here let A is equal to sigma square I, B is equal to sigma s square H, C is equal to I, and D is equal to H transpose. Then we will have the test statistic. It will be sigma s square X transpose H transpose into 1 by sigma square I minus 1 by sigma to the power 4 sigma s square H into inverse of the matrix sigma s square H transpose H by sigma square plus I into H transpose and X, the observed data. But you know, H transpose, it is sigma n0 to n minus 1 cos square 2 pi f naught n, and sigma n0 to n minus 1 cos 2 pi f naught n sin 2 pi f naught n, and summation n0 to n minus 1 cos 2 pi f naught n sin 2 pi f naught n, and summation n0 to n minus 1 sin square 2 pi f naught n. If n is large and f is between 0 to 1 by 2, then we get summation n0 to n minus 1 cos square 2 pi f naught n. It will be equal to summation n0 to n minus 1 1 by 2 plus 1 by 2 cos 4 pi f naught n, and it will be approximately equal to n by 2, and summation n0 to n minus 1 cos 2 pi f naught n sin 2 pi f naught n, it will be equal to 1 by 2 summation n0 to n minus 1 sine 4 pi f naught n, and it will be approximately equal to 0, and summation n0 to n minus 1 sine square 2 pi f naught n, it will be equal to summation n0 to n minus 1 1 by 2 minus 1 by 2 cos 4 pi f naught n, and it will be approximately equal to n by 2. So H transpose, it will be approximately equal to n by 2 and identity matrix I. So the test statistic, it will be sigma s square x transpose H transpose into 1 by sigma square I minus sigma s square by sigma s to the power 4 H into 1 by n sigma s square by 2 sigma square plus 1 into identity matrix I H transpose X, and we can write it as sigma s square by sigma square X transpose H transpose X minus n sigma square by 2 sigma square divided by n sigma s is to the power 4 by 2 sigma square plus 1 X transpose H transpose X. So the test statistic, it will be C by n X transpose H transpose X. This is the covariance matrix C, where C is n sigma s square divided by n sigma s square by 2 plus sigma square greater than 0. So I can write the test statistic as Tx is equal to C by n and the square of the Euclidean norm of H transpose X, or you can also write as T dash X, it will be 1 by n and square of the Euclidean norm H transpose X greater than equal to gamma double dash by C, or you can write it as T dash X, it will be greater than less than gamma triple dash, and triple dash it is gamma triple dash is gamma double dash by C, or you can write the the test statistic T dash X, it will be 1 by n and the square of the Euclidean norm with element n summation n0 to n minus 1 xn cos 2 pi f naught n and summation n0 to n minus 1 xn sin 2 pi f naught n. So we can also write this T dash X as 1 by n summation n0 to n minus 1 xn cos 2 pi f naught n whole square plus summation n0 to n minus 1 xn sin 2 pi f naught n whole square. Consider this part is I, summation n0 to n minus 1 xn cos 2 pi f naught n is equal to I, and summation n0 to n minus 1 xn sin 2 pi f naught n, it is Q. So I can write in the exponential form this test statistic as T dash X, it will be 1 by n summation n0 to n minus 1 xn is to the power minus j 2 pi f naught n. This is equation first consider, and this consider the equation second. So the detector for the Rayleigh fading channel, the block diagram of the detector for the Rayleigh fading channel. So for the quadrature or incoherent meshed filter case, if this is 1 by n, this is summation n0 to n minus 1 xn is to the power minus j2 pi f naught n, or it is summation n0 to n minus 1 xn cos 2 pi f naught n whole square, and summation n0 to n minus 1 xn sin 2 pi f naught n whole square. So first of all, we have to combine xn cos 2 pi f naught n, and other side we have to combine xn, the data, the observed data with the sine 2 pi f naught n, or combinedly we can combine xn with the exponential function e to the power minus j2 pi f naught. So first we will consider the equation first case and try to draw the block diagram for this. So for this equation first, the block diagram will be, first we will consider the observed data, then combine it with cos 2 pi f naught n, and on the other side we also combine this sine 2 pi f naught n. Then we will take the summation of these both individually, summation n0 to n minus 1 xn cos 2 pi f naught n, and on the other side we will take the summation n0 to n minus 1 xn sine 2 pi f naught n, and after this we will take the square of this summation part here separately, and from this after combining these two we will get the test statistic t dash x, and then we compare this test statistic with the threshold value, and if this exceed the threshold value, then we consider that hypothesis h1 is true. Otherwise we will consider that hypothesis h0 is true. And for the second equation was in this we consider the observation xn and combine it with the exponential function e to the power minus j2 pi f naught n. Then take the summation of this from 0 to n0 to n minus 1, then you should take the square of this and we will get the t dash x, and compare this t dash x with the threshold value, and we can get the hypothesis h1 or hypothesis h0 based on the value of the test statistic. If it will exceed the threshold value, then we will decide h1, and or if less than, then we will decide h0. In the first implementation, in this first circuit, we correlate the data with the cosine or you can say in phase, and with the sine quadrature replicas. Since the phase is random, one or both of the outputs I and Q will be large. So in this case the output here, it is I and it is Q, so it will be large in the magnitude, and if the signal is present, since the sign of the correlator output can be positive or negative, so we square the I and Q outputs and sum to get the test statistic. This type of detector is known as a quadrature matched filter or an incoherent match filter. The second implementation is the periodogram detector. The Fourier transform of xn is computed. Here this is the Fourier transform. Here it is computed, which is followed by the magnitude squared operation. So after this Fourier transform, this operation is known as Fourier transform, and after this Fourier transform operation, we will have the magnitude squared operation and scaling by 1 by n, and compare this with the threshold value. The Fourier transform is implemented as the fast Fourier transform FFT. Now, the probability of false alarm, it will be the probability of t dash x greater than gamma triple dash under hypothesis h0. So it will be the probability of the test statistic, it will be greater than gamma triple dash and under hypothesis h0. This is t dash x, and it will be equal to e to the power minus gamma double dash by 2 alpha naught, where alpha naught is lambda s naught sigma square by lambda s naught plus sigma square, and it is equal to n sigma s square by 2 divided by n sigma s square by 2 plus sigma square. So here it can be written as c sigma square by 2, and c is here, it is n sigma s square by n sigma s square plus sigma square. This part is c, and gamma double dash is the c gamma triple dash. So the probability of false alarm, it will be e to the power minus gamma triple dash by sigma square, or you can say gamma triple dash, it will be equal to sigma square log e1 by pf, and the probability of detection, it will be e to the power minus gamma triple dash by n sigma s square by 2 plus sigma square. Now to relate PF and PD, probability of false alarm and probability of detection, let eta bar it is equal to n expected value of a square by 2 divided by sigma square, or this is the average energy to noise ratio, and the expected signal energy, it will be n expected value of a square by 2, or you can say n sigma s square, because so the probability of detection, it will be the probability of false alarm is pf is to the power 1 by 1 plus n bar by 2, and you can also write it as pf is to the power 1 by 1 plus epsilon bar by 2 sigma square. So the probability of detection increases very slowly with increased eta bar, or you can say the curve of ENR, energy to noise ratio in dB, and the probability of detection. You can see the if we can increase the probability of detection by increasing the energy to noise ratio and or by increasing the probability of false alarm. Now we will consider the case incoherent FSK for a multipath channel. Let us take another example of communication through a multipath channel, and there are two hypotheses. H naught, it will be H naught corresponds to xn is equal to a naught cos 2 pi f naught n plus phi naught plus omega n, and H1 corresponds to xn is equal to a1 cos 2 pi f naught n plus phi 1 plus omega n, where small n is from 0 to n minus 1. Consider the problem of detecting the signal S naught n is equal to cos 2 pi f naught n, or S1n cos 2 pi f1n. Here for the hypothesis H1, it is a1 cos 2 pi f1n. So after propagating through the Rayleigh fading channel, and also assume f0 is between 0 to 1 by 2 and f1 also between 0 to 1 by 2, and n is large. Here omega n is the white Gaussian noise with mean 0 and variance sigma square. Now design the receiver to minimize the probability of error. So assume that the Rayleigh fading model for the sinusoidal amplitude and phase and the PDF of A naught phi naught transpose is same as the PDF of A1 phi 1 transpose. We wish to design a receiver to minimize the probability of error. For equal prior probabilities of transmission of each signal, we should decide H1 or H0 if the likelihood ratio means the conditional PDF under hypothesis H1 divided by conditional PDF under hypothesis H0, it will be greater than less than 1. Or I can write the conditional PDF under hypothesis H1, it will be 1 by 2 pi to the power n by 2 into 1 by determinant is to the power 1 by 2 and CS1 plus sigma square I into is to the power minus 1 by 2 x transpose, and the inverse of the matrix CS1 plus sigma square I x divided by the conditional PDF under hypothesis H0, it is 1 by 2 pi to the power n by 2 into 1 by determinant is to the power half CS0 plus sigma square I into e to the power minus 1 by 2 x transpose and the inverse of the matrix C S naught plus sigma square I into x, and it will be greater than less than 1. Let H1 is the n by 2 observation matrix. Let Hi is n by 2 observation matrix of the linear model based on the frequency Fi. So CSI will be equal to Hi theta I Hi transpose, and it will be equal to sigma s square Hi transpose, and the determinant of the matrix CSI plus sigma square I, it will be equal to determinant of the matrix CS square Hi transpose plus sigma square I. So it will be approximately equal to the determinant of sigma s square into n by 2 I2 plus sigma square I2, and so the likelihood ratio Lx, it will be equal to e to the power minus 1 by 2 x transpose and the inverse of the matrix CS1 plus sigma square I into x divided by e to the power minus 1 by 2 x transpose CS0 plus sigma square I inverse x, and it will be greater than or less than threshold value 1. So we can also write it as x transpose S1 cap greater than less than x transpose S0 cap, and we can also write it as IF1 periodogram IF1 greater than less than periodogram IF0. So the block diagram of the receiver, because we are using periodogram IF1 and IF0. So first of all, we will consider observed data xn. Then it will be combined with cos 2 pi f0 and sin 2 pi f0. Take the summation from n0 to n minus 1 separately. Then take the mod square and scale by 1 by n. And after this, we will get IF1 and IF0 periodogram. Then combine this, we will get the test statistic and compare it with the value 0, and if this is greater than 0, then we will decide in favor of test statistic H1. Now compare this with the threshold value 0, and if this is greater than 0, then we will decide in favor of hypothesis H1, and if it is less than 0, then we will decide in favor of H0. And this 0 is because we will take because here the threshold value is 1, and after taking the natural log, it will be equal to 0. Now to determine the probability of error, we assume that the frequencies are chosen so that IF1 is unaffected by the signal at F0 and vice versa. So if the mode of F1 minus F2 is very greater than n, here it is greater than n, then for equal prior probabilities of the signal transmission, then the probability of error, it will be 1 by 2 conditional probability H1 by when H0 is given plus probability of H0 when H1 is given. And by symmetry, PH0 by H1 will be equal to PH1 by H0. Then the probability of error PH0 by H1, it will be the probability of periodogram IF0 greater than periodogram IF1 given H1. So it will be integration from 0 to infinity, probability of IH1 less than T given H1 into probability of IF0 into P IF0 T by H1 dt, where this P if naught T by H1 is the conditional PDF of if naught. On having H1 occur, it will be equal to 1 by sigma square e to the power minus P by sigma square. So the probability of error will be approximately equal to 1 by 2 plus eta bar by 2, where eta bar is epsilon bar by sigma square. So the probability of error will be Q function of under root epsilon by 2 sigma square. So you can say that it is the probability of error, and probability of error reduced very slowly with increasing the energy to noise ratio. In many communication systems, the high error rate is unacceptable. To reduce it, we must use diversity techniques like frequency diversity, time diversity, etc. Now, so far in this lecture, we have discussed about Bayesian linear model. This was 21st lecture of the lecture series of random processes detection and estimation. In the next lecture, we will discuss about general Gaussian detection and detection of Gaussian random signal with unknown parameters. Till then, thanks for listening this lecture. Thank you.